It's been nearly 80 days since the Starliner CFT-1 launch, and the astronauts are still stranded on the ISS. Well, such a major incident hasn't occurred in a long time. This event has reignited intense comparisons between spacecraft, and once again, SpaceX's Dragon stands out as a shining example of cutting-edge and superior design. So, what makes Dragon so advanced, and how does it surpass Boeing's Starliner and even NASA's Orion? Let's find out in today's episode. First, let's take a closer look at Boeing's Starliner interface. Starliner draws heavily from Boeing's extensive experience with programs like Apollo, the Space Shuttle, and NASA's ISS, as well as the Department of Defense's Orbital Express project. This explains why Starliner has such an old-school, nostalgic appearance compared to SpaceX's Dragon. Inside Starliner, you're greeted with a control panel filled with so many physical switches, reminiscent of an Apollo-era cockpit. Well, this made sense in the early days of space exploration, when most astronauts were recruited from the ranks of pilots, so having tangible, tactile controls was familiar to them. However, times have changed. The criteria for selecting astronauts have broadened significantly, and the abundance of physical switches is no longer a priority. In fact, arranging screens and numerous buttons for easy access without confusion during different flight phases is now a major challenge. We've been in the touchscreen era for quite some time now. Moreover, this control panel, packed with physical buttons, takes up a lot of space inside Starliner, making it feel so cramped, even though its volume is comparable to, well, actually, slightly larger than Dragon's. Despite Boeing's claims that Starliner boasts a high level of automation, its design still reflects a philosophy that requires astronauts to be heavily involved in operations. This very philosophy has played a major role in the severe issues Starliner is currently grappling with during the CFT-1 mission, when the spacecraft couldn't even undock from the ISS without manual intervention from Butch and Suni. Now, when we shift our focus to SpaceX's Dragon, we see a completely different and very futuristic approach. Crew Dragon boasts a sleek, modern appearance, far more polished than Starliner. While Dragon has a slightly smaller diameter than Starliner, it's taller and more streamlined. And inside, Dragon offers a spacious, minimalist, and much more contemporary feel. This has been achieved by minimizing manual components and optimizing the layout. Specifically, Dragon uses 3 large touchscreen displays and very few physical buttons, a stark contrast to Starliner's complex control panel. The touchscreens have the advantage of integrating hundreds of indicators and functions into a single, easily accessible interface right in front of the crew. This system is designed with high redundancy. If one screen fails, the other 2 can handle the same operations. Even in the unlikely event that all 3 screens fail, there are still physical buttons available for emergency situations. Just by looking at it, you can see that Dragon is designed with a very high level of automation. Throughout the journey, astronauts will have minimal involvement in the spacecraft's operations. You know what? Most commands are pre-programmed, and the spacecraft is primarily controlled from the ground. The use of multifunction displays, MFD, in Dragon reflects a trend that has been widely adopted in the aviation industry, both civilian and military, for decades. This shows that SpaceX has applied the most advanced lessons and technologies to their spacecraft. So by simply viewing, we can see that Starliner belongs to an earlier design generation compared to Dragon. It features more manual switches and quirky equipment scattered across the workspace. While it's a step up from the cockpits of older space shuttles or even the latest Soyuz capsules, the advancement isn't that significant. The comparison between Starliner and Dragon highlights 2 very different design philosophies in the space industry. Starliner seems to cling to traditional design principles with a heavy emphasis on astronaut involvement, while Dragon represents a more modern approach, optimizing space, increasing automation, and simplifying the user interface. It's not just Boeing's Starliner. We can also look at NASA's Orion and see similar design trends in its cockpit. Orion's cockpit appears rather classic, with a multitude of buttons surrounding the display screens. Well, this can be explained by the project's development timeline. Specifically, Orion was developed in the early 2000s, a time when touchscreen technology wasn't as prevalent as it is today. As a result, NASA opted for a safer approach, utilizing tried-and-true technologies that had been reliable for years, similar to what's used in various aircraft. More than that, Orion was built following traditional aerospace models, where each spacecraft is unique and requires individual adjustments. In contrast, SpaceX's Dragon was developed in the early 2010s when touchscreen technology had become more widespread. This allowed Dragon to have a much more modern and user-friendly interface. However, when compared to Dragon, it's Orion's heat shield that really puts it at a disadvantage. Orion uses AVCOAT, an ablative material designed to endure and burn away under intense heat, protecting the spacecraft from destruction. Similarly, SpaceX's Dragon employs an ablative technology known as PICA, phenolic impregnated carbon ablator, which was originally developed by NASA themselves. Despite using the same type of ablative material, the performance of the heat shields on these two spacecraft is starkly contrasting. Right now, Artemis II is facing delays because NASA engineers are struggling to understand the issues with Orion's AVCOAT heat shield. After its return from the Artemis Y mission, the experts found that the shield didn't perform as expected, and despite numerous ground tests, NASA engineers haven't yet pinpointed the problem or found a solution. In contrast, SpaceX's Dragon continues to shine with the stability and reliability of its heat shield. Dragon has successfully completed dozens of missions, and not once has its heat shield failed to perform. Sure, Crew Dragon re-enters at a speed of 7.88 km/s, while Orion returns at a blistering 11 km/s, subjecting its heat shield to higher temperatures. But let's not forget that PICA was first developed and used on the Stardust mission, which re-entered Earth's atmosphere at an even higher speed of 14 km/s. So in fact, the comparison isn't out of line. Well, it seems NASA experts might not fully grasp their own technology after all. To be fair, Starliner is designed for land-based landings with parachutes and airbag, which facilitates easier refurbishment and maintenance. Boeing claims Starliner can be reused up to 10 times. Meanwhile, Orion is built for deep space missions, like trips to the moon, rather than low Earth orbit like Dragon. However, the key issue here is reliability. Always reliability. We can't discuss the potential for distant missions when the spacecraft can't even complete basic tasks. Clearly, both Starliner and Orion are falling short, with slow development and skyrocketing costs. Real reasons behind the shortcomings. So what's behind the struggles of Boeing's Starliner and NASA's Orion when stacked up against SpaceX's Dragon? Both Starliner and Orion are products of some of the most experienced aerospace giants, Boeing and Lockheed Martin. But here's the catch. They're often bogged down by outdated processes and technologies. These legacy systems make it challenging for them to adapt quickly to new requirements and innovation. And the most important factor in their difficulties is the complexity of project management within NASA and Boeing. Let me explain. Their projects typically involve a web of subcontractors. Take Starliner, for example. Boeing isn't working alone. They've got Rocketdyne and TechValve handling the valves and thruster systems, which have been the major source of issues for Starliner's CST-100 mission right now. Similarly, with Orion, Lockheed Martin is the primary contractor responsible for designing, developing, testing, and producing the spacecraft. But more than that, there are contributions from Aerojet Rocketdyne for propulsion systems, ESA, Honeywell, and others. Each contractor within these programs has its own subcontractors, creating a complex and intricate network. Each company has its own production processes and quality standards, making the synchronization and quality assurance of assembled parts extremely complicated. This is the crux of the issue that both Boeing and NASA are facing. They are entangled in endless testing and discussions without reaching definitive conclusions about the problems their spacecraft encounter. In stark contrast to the dispersed, subcontractor-heavy approach of its competitors, SpaceX is renowned for its vertical integration philosophy. This means SpaceX manufactures the vast majority of its parts and vehicles in-house, rather than relying heavily on external suppliers. This approach grants SpaceX unparalleled control over quality, costs, and project timelines. SpaceX's primary manufacturing facility in Hawthorne, California, is one of the few places globally where you can witness an entire rocket or spacecraft being assembled under one roof. This is a dramatic departure from traditional aerospace companies, which often depend on a complex network of suppliers. Thanks to this philosophy, SpaceX's engineers and staff have an intimate understanding of every detail and step in the production process. They possess comprehensive knowledge of procedures and quality standards, instead of having to coordinate with multiple external entities. This fosters a unified and tightly controlled development process. Any issues or setbacks are identified and resolved swiftly on site, avoiding the convoluted mess that often plagues their competitors. All right, that's it for today. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more in-depth looks at the latest advancements in space technology. Thanks for watching, and I'll see you next time.